Morning, everyone. So this is the transport session. We've got 3 speakers today. So our first speaker had a signal failure on the train, so he's going to join us from Zoom. Hopefully everything's set up. So we'll get straight on it. So our first speaker is Muir from the University of Manchester. He's a postdoc there at the Tyndall Centre, and his research focuses on the carbon optimal and fiscally optimal modelling and simulation of BECCS, as well as other CCS supply chains. His research takes a particular interest in developing CCS integration pathways for dispersed emitters, utilising a mixture of pipeline and non-pipeline transportation methods. Okay, Mia? Yeah? I'll hand it over to you.
There we go. Sorry about that. So when I screen shared my new, are you able to hear me? Perfect, great. So thank you very much for inviting me here. Sorry about not making it in person. There were some delays with the trains. So I'm going to be presenting a nice presentation for you for a project that we're doing with the UKCCSRC flexible funding, where we are connecting dispersed emitters for cement into the UK's CCS networks. So you can see here as a little amuse-bouche to what sort of modelling capabilities we have at Manchester is. These are the integration pathways for all of the CCS capable emitters in the UK, producing more than 1,000 tonnes per year, integrated into the geological storage sites across the UK using a mixture of pipeline and non-pipeline methodologies. So today we're here to basically connect these cement emitters, these cement facilities, into these offshore geological storage sites using a mixture of HGVs, rail, pipelines, and shipping. It is very important for these sites to be connected in, as some of them are very large emitters and do not have an immediately available connection point into these offshore geological storage sites. And the objective of this project is to connect them by minimizing your transportation costs and your transportation carbon for that. So to be able to do this, we're utilizing a model that was created for another project called the Carbon Navigation System. It was designed for bioenergy, carbon capture and storage supply chains, but it has been repurposed and has worked a dream on cement facilities. So it's a high spatial resolution digital twin of the UK CCS and transportation freight networks, and is able to automatically switch between HGVs, rail, shipping, and pipelines to minimize your carbon and your fiscal transportation costs. Interestingly, there are applications for the other limbs of the model. So the model itself is built up of 4 different limbs, all tailored to model different aspects of a supply chain, be that the finding and sourcing of biomass, the exportation of hydrogen into your hydrogen networks, or your onshore salt cavern storage, or your energy outputs. If you're producing a sort of energy fuel like a biofuel or a hydrogen or other, you can send that to your end user. But for today, we're only using the CO2 limb, which is where you're able to plug in a facility in the UK. It will automatically switch between these transportation methods, connect to an industrial CCS cluster, and connect you to a geological storage site wherever you want to be in the UK. This is already applied to a few industries across the UK, so it's already applied to BECCS, to glass, to cement now, but also some chemical industries as well. If you want to know more about this model, I've copied down the Frontiers in Climate paper we've done recently, and also a policy blog with the Policy at Manchester team. So the cement integration framework for this project, we geospatially found all the cement facilities, cement and lime facilities, imported them into the model, the Carbon Navigation System model, and then did some carbon optimal and fiscally optimal modeling, changing the carbon intensity of HGVs, rail, shipping, pipelines, and the fiscal intensities of the same transportation methods to be able to inform decision-making for industry and policymakers, to highlight what your integration pathways are, your network flexibility, and the vulnerabilities and opportunities you have as a dispersed emitter to connect into these CCS networks. and importantly, which clusters you want to connect to and what your flexibility options for that. So from that, you get these decision dashboards to where you're able to see the integration pathways for your cement facilities. So over in diagram A, these are all the cement and lime sites integrated with using a carbon optimal integration. This is minimizing your carbon emissions integrating into storage sites. Number B, the table B just shows you your name, your operator, your sector that you're going from, whether or not you are a centralized CCS track 1 facility, which there are 3, or if you were a dispersed site. It tells you what your capture potential is for your facility, how much your carbon cost of integration is going to be in kilograms of CO2 per ton of CO2 transported, the distance you traveled, what storage site you're going towards, and which clusters you accessed as a dispersed emitter. You may be forced to integrate through multiple clusters to be able to access your storage site, as is the case with Aberthaw, which you're accessing through the South Wales cluster, then the Northwest cluster. And then diagram C, you can see what proportion of your emissions came from what form transportation method. So you can see that quite a vast amount of these emissions come from your HGV integrations. We did exactly the same with the fiscally optimal. So this is the exact same data, but showing you how much it costs in terms of pounds per ton of CO2 transported for each of these emitters connecting to you to offshore geological storage site, as well as the breakdown of that cost. You may look at this as the diagram C, as a lot of your cost is coming from HGV, and especially for these centralized track 1 facilities, why won't these have a pipeline connected that just to eliminate these high cost HGVs? That is coming. We are only 7 weeks into this project, and that data is calculating right now. So this is, we're giving options to show you what are your options right now. So it's assuming a 2030 level of infrastructure and what infrastructure is going to be put in place for that. And then we also give you options for what if you put in additional pipelines. So what if you have your integration pathway, you replace your short distance HGVs with pipelines as one option, as well as where it makes sense to eliminate all modes of non-pipeline transportation with a pipeline where it may be the case for facilities like Hope Cement. So it gives you these options, but that data is coming since we're only 7 weeks in. But from that, it's really quite important to know what your network flexibility options are for each of your facilities, as your access to your storage sites may go down. It could be down to access to the pipelines may go down. There could be some maintenance going offshore, or there could be some sort of variance in your flow rate within pipelines forcing you to access another pipeline or another cluster. You can see that green is good, red is bad with this the table to the right. But the main advantage of being a dispersed site is that you have increased flexibility options for your emitters. If you are a track 1 CCS facility, you're kind of hard locked into your storage site, especially if you're in the Northwest cluster, where right now you only have access to the Hamilton site, compared to in the Humber, where you have originally you only had access to the Endurance sites, but the addition of the Viking cluster with access to the Viking A facility has given you increased flexibility options there. So it would be a major advantage for the Morecambe sites to be opened up in the East Irish Bay to give you those increased flexibility options for that. So as if you do not have that open, in the worst case scenario, you are increasing your cost of transportation by 724%. So it's really quite fiscally and carbon intensive to get these other options in the worst case scenario. But it's quite valuable information to give to these cement and lime facilities to know what your options are for flexibility. And again, with that, there may be a wide range of variables that might impact your integration pathways. So you could be using a slightly different size vehicle. So you can use a big ship, small ship, or you can introduce decarbonized fuels into your CCS networks that may impact which modes of transportation you're choosing. So you can see that we've done these simulations for HGVs, rail, shipping, and pipelines, just showing you the carbon intensity ranges. What happens if you put in something a bit more carbon intensive? What happens if you put in something a bit less carbon intensive? Just to be able to show that some forms of transportation are more impactful than others, as for HGVs and pipelines are always used in these integration pathways. So these are quite impactful things to take note of, and these are your vulnerabilities, whereas the majority of your cement facilities are widely unimpacted by shipping, unless you're Aberthaw or Dunbar Cement. We've done these exactly same things for the fiscal costs. So what happens if the cost of your transportation depletes, so we have huge advancements in the reduction of the cost of transportation, or what happens if we have events similar to the war in Ukraine, where the cost of fuels massively increases. Does that shift you away? An interesting case study for this is Aberthaw, where you want to use shipping for your integration to be able to access from the South Wales cluster into the Northwest. But when the cost of shipping transportation becomes a certain point, you can see that these lines plateau, brown for Aberthaw. They plateau as the model is smart enough to say, hold on, these costs are too much. We're going to have to integrate using another method. So if you're Aberthaw and the cost of shipping goes too high, you swap to rail transportation to integrate in. It gives you these options, be that a constant increase in cost or maybe a sort of shock to the system. It shows you what your flexibility options are depending on these external variables. Hope I'm doing okay on time. But then you can show these sort of impacts for these cement facilities, whether, are you able to see my mouse? Yes, I can see. Okay, perfect. So what happens if you integrate your system with low-cost HGVs, high-cost HGVs, and the same for rail here, low-cost, high-cost, shipping, low-cost, high-cost, low-cost, high-cost pipelines as well, just showing you how in many facilities you're kind of flip-flopping between which clusters and which storage sites you're accessing. And it can really vary and it shows these cement and lime facilities. Depending on these future variables, what level of infrastructure do you want to set up now so that you have good options as the whole system may flip? Whereas if you set up now for, say, if you're Hope Cement accessing the endurance field, and eventually the cost of HGVs goes dramatically down, and the modeling shows that you're actually better off going to the Northwest cluster. It shows you these flexibility options, what your threats and opportunities are for these sites. Just to expand this, to give it a bit more visually, you can see that is a sort of threat and opportunity diagrams to show you green is good, red is bad. And it showed you that a lot of the cement sites are vulnerable to HGVs and rail as their major proponents for their threats and opportunities, whether or not you increase the carbon intensity or the physical intensity of the transport methods by decreasing it by 50% or increasing it by 50%. These are the most vulnerable, these are the most sensitive aspects you're looking at. So these sort of integration hierarchies, which ones make good candidates to integrate? So it makes sense to integrate your Track 1 CCS centralized facilities in the Northwest and the Humber clusters. It makes sense for that. But in terms of the dispersed facilities, you want to look at Whitwell, Hope Cement, and New Rugby, as these are good candidates to integrate first, as well as setting up a potential cement cluster around Hope Cement that could potentially integrate the other cement and lime facilities around that. But it is important that there may be additional CO2 pipelines integrated into these systems, as Hope Cement could use either a mixture of HGV, rail, and pipelines, or you can replace that whole integration pathway by a mixture of just rail and pipeline, or potentially just pipeline. But these are mostly hindered by the non-technical limitations on these integration pathways. How many trucks can you have on the road? How many rail cars can you have on your tracks? So there's a further discussion to have on that. So to conclude, the integration pathways to implement the pilot and the full-scale phases of cement integration, you require a mixture of your pipeline and non-pipeline transportation methods to be able to access these sites, especially if you're a dispersed emitter. But most importantly, collaboration between the clusters is vital to ensure flexibility between that. If you are locked into the Northwest cluster and you need to store somewhere else, you're going to incur huge carbon fiscal costs integrating into another cluster, and you need that collaboration and that capacity loading building to be able to integrate into those systems. But you may have other factors. That flexibility is just one of the major factors and one of the main advantages of being a dispersed emitter, and you need to be able to capitalize on that and build the level of infrastructure to be able to do this in the future. Thank you very much.
Thank you, Muir. Do we have any questions? Can start. So, did you think about the timing of all this? So, when sources will come online, when the infrastructure will be in place, is that included in your model?
Yes, it is. So the sort of initial level of infrastructure, the main trunk lines for all the clusters, they have, have I muted? Okay, good. So it's assumed for about 2030 level, but a lot of we've talked to a couple of cement facilities. I've called them up. We've had meetings with them. I've actually called up them Bar Cement on the phone. We've asked what sort of timelines are you expecting for that? They have been a little bit nondescript, but they are saying around or just before 2030. So these are accurate models, but then you do time that into the integration of your decarbonized fuels or your low cost, high cost fuels, because potentially modeling future situations, future network scenarios to see what sort of options do you have in the future. So you can set up for both now and make sure that infrastructure that you put in now, that those additional rails, ships, pipelines, will they still make sense in the future?
Do you include the costs of storage? Do the costs of storage vary depending on the field that you choose, or were they uniform?
What was that? Sorry, I think it cut out a bit. The uniform. Sorry.
Right. So about the costs of the storage. So you were thinking you could go to different sites for the storage depending on the timing. Did the cost of storage vary depending on site? Was it site specific or was it a uniform cost?
So that's not included in the model. So this is mostly the transportation aspects of that. So that is another external variable that if the cost of storage for one site becomes too high, you can easily add that into the model and show, even though it makes low carbon sense or low fiscal sense to integrate into this cluster, the cost of storage is too high. Let's integrate into another one where it may be a little bit more carbon intensive, but with the lower cost of storage, you may integrate into that. So that's easily added into the model.
Thanks. Any question from Aaron at the back?
Aaron Goethe from Beringer. I was interested in how you model the rail option. If, for example, a site is, say, I don't know, 200 meters from a rail connection, what do you sort of assume? Do you assume that sort of public land? Is it how does the CO2 kind of get from the site to a rail connection, or how do you more broadly model it? Because I guess a lot of sites won't necessarily sit right on a rail connection, but they might be sort of nearby.
So within the model, you choose specific points at which you're able to transition from one mode to another. So if you are a cement facility or any sort of facility that is somewhat near a rail terminal, so these are the points that you can access onto the rail infrastructure, you would have to use HGV to connect your facility to the rail infrastructure. You have facilities like New Rugby, which are really, really close to the rail terminals, where you can access that quite well. But right now, depending on the options that you present, you'd have to use a short distance HGV to connect to that rail terminal, or with the data that's modeling right now, you replace that short distance HGV with a short distance pipeline directly to the rail terminal, giving you you're increasing the rigidity of your integration pathway by putting in these pipelines, but you're still maintaining some flexibility with this rail as you're still able to divert to another cluster or not. But it is a huge advantage to connect your facilities to your rail terminals and to your ports via short distance pipeline to be able to increase that rigidity. But you need to connect into it. You can't just magically jump onto it.
We've got a couple of questions online. Arun, are you able to unmute to ask them? If not, I can do it. So his first question is, does your analysis include reliability?
No, it doesn't at the moment. So it's kind of flexibility was the main objective of this analysis, but reliability of that. So they do link towards that. So having the flexibility options and how reliable these integration pathways are, you do have points of failure to do that. So if you are a facility that is massively relying on let's go New Rugby, you'd be relying on rail connections to get to access to the storage site, but how reliable these sources are, that's a point of contention there. So that would that'd be valuable information for future study. But having those flexibility options in this work would show you if an integration pathway goes down, you have this sort of database of integration pathways that you can swap to be able to keep that low carbon, low cost for you. So if it does go bad, you've got another option.
Any more questions from the room? Questions on that? Okay. So we'd like to thank Muir again.
Thank you very much for having me.
Okay, next up we've got Jasmin. So we've got Jasmin Kemper from IEAGHG. She's a technical advisor there, and she's managed many technical studies including studies on CO2 dehydration, pipeline transportation, accounting for greenhouse gas emissions from CCS clusters, regional CCS developments, and unburnable carbon. So our other work areas include IEAGHG's network on solid looping technologies, sustainability issues, life cycle analyses, non-CO2 greenhouse gases, and CO2 utilization within geological formations. Over to you, Jasmin.
Thank you, Ben. I'm going to present today, if this works. On the status and challenges of CO2 shipping infrastructures. So Tim told you yesterday who we are. We are a technology collaboration program under the International Energy Agency's Energy Technology Network. And although we are kind of associated, we are autonomous, and so our views and findings do not necessarily present the view of the IEA Secretariat or in individual member countries. So the background to this study is that efficient carbon capture and storage at industrial scale depends on CO2 capture from relatively large point sources and transferring it to secure geological storage sites. And as this technology option expands, onshore pipeline networks will be necessary to deliver the volumes that we need to capture and store. However, not only pipelines, also shipping could offer a flexible and economic alternative, because usually the upfront costs are lower and you could probably deliver to a wider geographic network. So the shipping of CO2 has already been carried out for some decades for the food and beverage industry, but at a relatively small scale, like around 2,000 tons. And so establishing large-scale shipping operations would require the consideration of regulatory, technical, and economic conditions. And so we commissioned Element Energy to undertake an assessment of the status, costs, and challenges of CO2 shipping infrastructure in 2019. And they did this in collaboration with SINTEF, IOM Law, and Brevik Engineering. And the report is already published. So if you want to have a look in detail at the results, because we won't be able to go through everything that the report contains today, then please download it from our website. So we looked at the following three North Sea carbon capture and storage scenarios. And those scenarios compare low pressure with medium pressure conditions, and also onshore with offshore unloading. So those ship operational profiles have been estimated and used as the basis for shipping cost estimates. And the shipping costs are based on new built CO2 tankers. So not based on repurposed, for example, LPG tankers. And the costs were then combined with cost modeling of the onshore components to estimate the costs of the full shipping chain. So you can see on the map, like we assumed, like scenario one, we will ship from Rotterdam to Osnes in Norway. We will unload onshore at a terminal at low pressure conditions. And then there is a pipeline connecting that onshore terminal with the geological storage formation in the North Sea. Scenario number 2 is the same, just for medium pressure conditions. And then scenario 3A is shipping it from Rotterdam directly to the place of injection to a floating storage and injection platform. And scenario 3B is shipping it directly to the injection and directly injecting from the ship. So the ship is able to directly inject into the ship. So those are just it's just an overview of all the parameters for the techno-economic modeling, what we did consider. I'm not gonna spend a lot of time on reading all those out. You can read them later in the report if you want. So we will go directly to the cost results. So we assume 2 wells with a maximum injection rate each of 114 tons per hour, which would give us 1 million ton per year operation over the whole chain over the year. Offloading to onshore and offshore storage were assumed at a rate of 600 tons per hour. And offshore unloading includes an unavailability factor to reflect times when, for example, weather limitations would prevent offloading. This is important for the direct injection and also the offloading to the platform. And because offshore unloading has longer operational times, as you can see in the graphic on the left, than onshore loading, it contributes to like a lower volume of injected CO2 per year. So you can see here the round trip time for each scenario, and you can see that scenario 1 and 2, which offload to the onshore terminal, have a round trip time of about 138 hours per ship. And for the offloading to the platform, it's higher at 150, and then for the direct injections, it's even higher at 178 hours. And this is due to the unloading availability and the larger time needed for unloading itself. And so you see that this means that the scenarios will deliver different injection volumes per year, assuming 3 ships are used. So the first 2 scenarios are able to deliver 1.8 million tons per year. Scenario 3A, 1.7 million tons per year, and scenario 3B, only 1.4 million tons per year. Then we added an illustrative cost of a shore to offshore pipeline to scenarios 1 and 2, because you remember we are only unloading on an onshore terminal. So we then need to consider what the cost of the pipeline to the storage formation. And the cost of onshore infrastructure were derived using a detailed factor estimation method to enable us to give the cost of the full shipping chains. And you can see the CAPEX and the OPEX with their breakdowns here on this slide for the different scenarios. And you can see one conclusion is that low pressure onshore unloading has the lowest CAPEX for the shipping part of the chain, but the additional cost of the onward pipeline transport brings the CAPEX above unloading to a floating platform. And direct injection has the lowest CAPEX and OPEX cost, but it also, we remember from the last slide, it stores the lowest amount of CO2. So, and here assuming what we did an allocation, so the full costs of the pipeline were allocated to the scenario. However, we can also say that is this really likely? Because in reality, you might have multiple projects using that one onshore terminal to offload. And so, yeah, if we assume that it is used by multiple projects, this will of course bring down the overall unit cost of shore-to-shore transport. So here we have the cost as euros per ton of CO2 for each scenario. And yeah, you can again see that the pipeline can add a significant chunk to that. And the study also looked into what if we assume lower pipeline costs, and we found that those 8 euros per ton CO2 for the pipeline can go down if you ramp up to a network that's able to deliver 10 million tons per year. They could go down to 3 euros per ton. So on this slide, you can see what happens if we increase ship size above the generally assumed 10K tons of CO2, and we found that this does not really significantly reduce the cost. So here it is depicted for onshore unloading at the rate of 600 tons per hour, unloading to the platform at 600 tons per hour, and direct injections unloading at 228 tons per hour. And yeah, you can see that there is at around 10K ship size, there's already kind of an optimum, and later you can see that the costs start going up already again. And then we looked at what would happen if we could unload and inject at a much higher rate for a different scenario. And with higher unloading rates, increasing the ship size above 10,000 tons CO2 can reduce the costs, but only if the number of ships is reduced at the same time. However, we have to keep in mind for those high unloading and injection rate scenarios that they are really more challenging to achieve, especially for a ship that directly injects into the storage reservoir, because this is still kind of unproven technology. So offloading to a terminal to onshore is kind of proven technology, but floating platforms and direct injection are still pretty much not technically demonstrated. So we then did a comparison of pipeline versus ship transportation costs, and the pipeline transportation costs decreased to a much higher extent with the annual flow rate than the shipping transport costs. I assume no surprise here. And this is due to the fact that pipeline costs are dominated by CapEx, whereas shipping costs, on the other hand, are dominated by OpEx and fuel costs. So you can see here the unit costs of pipelines going down as the flow rate ramps up, and the ones for shipping stay pretty much similar. And yeah, at one point you then, of course, have a break-even point where the ship becomes more expensive than the pipeline at around above 2 million tons per year. And so, yeah, shipping is more cost effective than pipeline transport at large transport distances and at low flow rates, as this example for onshore unloading shows. And on the left side, we have a flow rate of 1 million ton, right side 2 million tons, and you can see here the break-even points where the pipeline is, the ship is more cost effective. It's depending on whether you have a non-pressurized or pre-pressurized ship. And the same also applies to the direct injection cases. And I apologize, I think the second line for ship pre-pressurized doesn't show here. It's similar to the diagrams before. It runs parallel to the orange line, just further down where the 450 and 620 break-even point is. Then we also did an assessment of regulations, and we already talked a lot about that yesterday in the plenary discussions. I'm not going to spend a lot of time here. So, well, naturally, not a lot of hurdles were identified. The only hurdles identified were potentially the London Protocol, the ETS directive, and the Norwegian GHG Emissions Act, because we are injecting in a Norwegian localities. So, and as the GHG Emissions Trading Act is drawing from the ETS directive, so any potential hurdles from the ETS directive would also be present in the GHG Emissions Trading Act. But this study started in 2019, and you might remember from yesterday, 2019 was a year where a lot happened in the London Protocol, so that hurdle is more or less has come down. And also we told you that the ETS directive has now been amended to include maritime shipping emissions. So conclusions. The transport condition of CO2 affects a large number of components of the shipping chain, including the material choices, storage tank designs, operation, transport modes, and safety considerations. Onshore infrastructure is generally well understood, whereas offshore unloading and injecting directly is currently unproven. Batch-wise injection especially presents challenges for offshore unloading. but maintaining a continuous flow requires the use of a floating platform, which is a major cost driver. So you either have the more challenging option, direct injection, or you could just spend more money on a injection platform, which is thought to have less technical challenges. For representative CCS shipping chains in Europe, undiscounted unit costs of around 30 to 40 tons per CO2 are projected. And liquefaction and ship costs make up the majority of the cost breakdown in the shipping chain. And also we found increasing the ship capacity and or the unloading rate reduces costs only if the number of ships in the chain can be reduced at the same time. The break-even distance at which shipping becomes cost competitive with pipeline depends on the flow rate and pressurization. International, regional, and national legal frameworks present few hurdles, and I've just told you the update on that. And what I was asked yesterday, and I've not gone in detail into this, but a small assessment of this was included in the report. Contractual arrangements may be based on existing frameworks, but specific clauses will need to be included. So the study identified there could be 3 models that are already used that would be usable also for CO2 shipping, such as I think it was a voyage charter, time charter, and bareboat charter. And one of the main issues that needs construction legally is the liability of CO2. And also there needs to be probably provisions, and they are already in shipping provisions for future changes to the ship. So even if you have not a repurpose but a new built CO2 ship, you might need to make some changes in the future, and those are usually part of the contracts. And so the report is also something what to say on this. And one important thing is that ship operators will probably have to manage these 2 reporting schemes for CO2 emissions from fuel. But at the point where the study was done, CO2 leakage from cargo and injection into the seabed were not covered. But as we are aware, in the EU ETS and CCS directive, there are already kind of discussions underway to also include those in the future. So yeah, that was it for me. So thank you. If you have any questions, I'll try to answer.
Okay, so time for question.
Thank you for your lecture. I work for the insurance industry covering the ship owner's liability. So I'm very keen on this issue in terms of the transportation by shipping. Do you have any ideas what kind of risks involved in the transportation of the ship? So from the insurance point of view, we are very much interested in the risks involved. So what kind of damage and loss will be anticipated for the shipping? Do you have any major casualty case before or ongoing cases? Do you have any ideas on this?
I must admit, I'm not a shipping expert, and I also didn't manage this study. The study was managed by my colleague who is now retired. So I would need to check back with the contractor if they have maybe they're also, because this study was done in 2019, right? So there might have been updates on that topic. I only know that the liability and contractual things, they were covered in the report, but they were not like the main focus of the report. So the main focus was the techno-economic analysis. So I need to refer, to come back to you by email. I mean, some of the risk involved by the ship and the that would mean, you would emit CO2 to the atmosphere, which would be penalized under the scheme that you are under, right? There could potentially be material failures, but depending, especially if you are maybe using a land-purpose ship, it's possible to use LPG ships. There are some challenges, depending on how much CO2 you will then load, and so yeah.
Yes. As far as I understand, the Northern Lights project is now have just started or just at the beginning stage. So our entire vessels have already been engaged in the operation in the Northern Lights projects. You haven't heard anything about any accidents or casualties
I'm not
in the
I'm not
that
aware of
project?
any accidents. I know that US, they have a kind of pipeline hazards database, so you can look up pipeline accidents and fatalities for CO2 pipelines, natural gas pipelines, and other pipelines. I'm not aware that something like this exists for shipping, but as I said, I'm also not an expert on shipping in particular. So yeah.
Thanks. You studied about the shipping side. Did you have any contacts?
I mean, the study or the report also looked at ship designs in the first sections of the report, and I think one of the subcontractors, Graphic Engineering, I think they are involved in designing ships. So the first picture of the ship I showed in the background slide, that is actually one of their, I think, designed ships. So yeah, we could try to bring you in contact with the subcontractor or other companies that might have been involved in acquiring data for the study.
Okay. Not involved, not a question on the same topic about whether there's been the safety studies. So things like this in the Norwegians involved in Northern Lights, and one of the questions we've had is that in terms of understanding risks of shipping, there's been experiments of releases of CO2, but all at ambient temperature, whereas these are considering refrigerated releases. And to my knowledge, there's never been experiments to understand what would actually happen if there was a release of refrigerated CO2. And those kind of accidents have happened in the past. So for LNG, for loading arm failures, there was an incident that took place in Barcelona. And if you think back to the work on LNG when it was first being used for shipping back in the 80s, there was a massive program of work undertaken in the US looking at spills of LNG underwater to study things like rapid phase transitions and explosions. That, to my knowledge, has never happened with CO2. So there's a knowledge gap there. Lloyd's Register or Lloyd's Foundation and DNV are probably some of the groups that would be good to talk to on this side. Yeah, if you
Yes,
hear on the IA,
I'm only aware that those release experiments have been done for pipelines, right? But I'm
Yeah.
not aware if they have been done for ships. Yeah.
This little bit and so another question, when you're doing shipping operations, do you have to kind of bunker or have buffer storage of CO2 at docksides? When you're filling ships, you don't want to have a very slow fill from a long pipeline.
Yeah.
So you'd have like a few tens of thousands of tons storage vessel at a port, which would have you considered the regulations around that so or land planning?
I think we have covered that in the study. I mean, if we can go back to the presentation. No, I can go back. All right. I have some backup slides. So someone asked about the examples for ships, and those are LPG ships repurposed for the carriage of CO2. So there are some company names or owners like Transtar, Sonoma, and Muir shipping. So those might starting points for you maybe to look more into it if you really want to reach out to to the companies that own and operate existing ships.
More question?
Thank you, Homewood Environment Agency. I'm just wondering about, you mentioned that it would take, your model shows the amount of CO2 being shipped to be about 10,000 tonnes. And I notice here on the slides, it's probably the equivalent there. I mean, do you think, how feasible is it for the ships to be able to ship more than 10,000 tonnes of CO2?
I mean, technically feasible, it should be. What we have seen in the cost analysis is at some point it reduces the cost, but then if you go to larger ships, it doesn't reduce further.
Right,
So
yeah.
Yeah.
Yeah, and I've just had another question, sorry. The floating platforms, you mentioned that hasn't been tested yet, the technology. Is that currently in sort of a development stage or?
I think it is in development stage, but I don't know who is testing it. I would assume
Okay.
because this study was done like 4 years ago that there probably was some development, but yeah.
Right. I'm just thinking, just imagine that happening at sea with the, really dangerous sea conditions.
Yeah,
And
that's
wondering,
why the unloading unavailability is important, or is an important
Yeah.
factor in the cost, because you have to
Right.
account for those
For
times where
those
you can't
times.
inject or unload because of bad weather or
yeah,
high tide or yeah.
right. Okay, lovely, thank you.
Thanks. Joey Scarf, Department of Energy Security and Net Zero. A specific point I was quite interested in was the proportion of the cost attributed to the liquefaction, which I think you had, was it about between a quarter and a third of the cost? And yeah, that was the slide. Yeah, I guess I was wondering, in some scenarios, you may need to compress the CO2 before your injection, even if using it. So if you use a shore-to-shore scenario, then the onshore pipeline, as it moves to the offshore, you may be seeing, you may have compression facilities anyway, I suppose. And you may be injecting in dense phase. So then, is that liquefaction cost an add-on, or could it be a replacement for a similar cost for the onshore pipeline? I.e., do you lose that energy used in the shipping when you unload, or can you keep it in liquefied state and inject without having a pressure loss? I'm not sure if I explained that particularly well.
I must say I'm not a geological storage person. I'm from the capture side, so I'm not sure if you could inject in liquefied state. I think not. I think I've never heard of it.
So I suppose that you wouldn't necessarily inject as is stored on the ship, but do you lose the energy inputted to get the CO2 to that state? I don't know if anyone else knows the answer, but
I'm not sure if anyone here is from the storage or injection expert side.
So do you mean that you have to chill your CO2 down to -50%?
Yeah.
But you don't inject it at -50 at a certain bar, you inject it at 130 bar and
I suppose so if you have like a regular plant on a pipeline, onshore pipeline, then you're going to run that CO2 through a bunch of compression facilities that's also going to cost significant energy and price. And so will you then have to repeat the procedure for something that has arrived by ship, or have you already moved through some of those stages in terms of compression?
Most of my ship, I think we put it in a small probably an intermediate storage vessel, I would have thought.
Yeah.
Which would also be refrigerated. But whether you can put it in the pipeline as it warms, it'll repressurize.
Yeah.
Sorry, I can't answer that question.
Any questions on that?
Yes, there are questions on that. I'm not sure if they are from. I think there's one question, the environmental cost footprint. No, we have not done any environmental and costing.
Quick question. Yeah, okay. Got time for one more quick one.
Hi, thank you very much. And my question is, do you have any idea if the shipping operations are run by one entity, or is it a traditional shipping context where you have a ship owner, seller, buyer, and so on.
It's contractual different
Yes.
models come into play because you can charter a ship and you can charter the crew with it, or you
Yeah.
can charter the bareboat, and then you can bring your own stuff on the ship. And some of those charters only let you transport the specific cargo, and some you're free to transport whatever cargo the ship is suitable to carry. So.
So from these examples, do you know if it's one entity or is it traditional? Do you have an idea about the operations that have happened already?
No, I mean,
No.
it might be in more detail in the report, but
I think it's good. Thank you.
Okay, we better wrap up there. So thank you, Jasmin. Okay, we'll try not to break it again. So lastly, we've got Julia Race from the University of Strathclyde. I'm going to go. So prior to academic career, Julia worked in industry for over 20 years. So as part of that, she was responsible for providing fit-for-purpose remaining life and corrosion assessments for onshore and offshore pipelines. She's also worked as a materials engineer in the petrochemical and power generation industry, involved with the operation, maintenance and design of chemical power plants. Her primary research interest is in the use of pipeline infrastructure to deliver net zero pathways, mostly through transportation of CO2 and hydrogen as well. Research topics include material and specification requirements for CO2 and hydrogen pipelines, techniques for conducting quantitative risk assessments, including pipeline failure frequency and consequence analysis, hydraulic network design, developing system flexibility, and techno-economics and wider economy impacts, which I think about you're going to talk about here. Right?
Yeah.
Over to you, Julia. Thanks.
So it's the last one I'm going to talk about today. Okay, so this is a paper that was accepted for International Journal of Greenhouse Gas Control, and it is a techno-economic cost assessment for carbon dioxide transport and storage implementation. But I'm not really going to talk about the model. I'm going to show you what the model is. Why we did this work was more interested in how you use that model. Because in order to do what we need to do, we need to introduce this new carbon dioxide transport and storage sector into the economy. And at the moment, this doesn't exist in the economy. And we wanted to understand what the impact of that was. So I've put two quotes up there from work done at the Centre for Energy Policy, where we've used this model that I'm going to describe to you, and we've looked at Track 1 cluster projects and Track 1 cluster and the Grangemouth cluster in Scotland, to look at what would be the impact of introducing this transport and storage sector into the economy. And so I've just put that up as a kind of teaser that I'm going to come back to, because when we're doing all this techno-economic modelling, it really what we wanted to understand was what benefit does that have in the wider economy. So we have, using this model, introduced a transport and storage sector into the economy, into an economic whole economy model. So this is what this model is designed to do. We published this in 2021, and since then things have moved on, and we are now in a stage of refining this model in the light of announcements that have been, and maybe announcements that are to come. But I guess one of the key takeaways from this is that introducing this carbon and transport sector into the economy could trigger green growth in terms of GDP, but it is and jobs, but it is very dependent on who pays for it. So what we have looked at is just the transport and storage part of this sector definition. In the model, in the economic whole economy model, which is called the CGE model, so I'll refer to it as that. In the CGE model, we model capture in a different way, but transport and storage, we have models looking at the network of onshore and offshore pipelines that we would need to transport the CO2 emissions from each of the clusters, using shipping where that was a viable option, but not using rail or road transport. And as we've seen today, therefore, we have not included the dispersed emitters, but certainly in Scotland, it is something that we will need to do because of dispersed emissions around the country and the nature of the geography, particularly industries like the whisky industry, where the whisky industry can't move, it has to be where it is. So we're going to be looking at that as well. So we're looking at the transport and the storage. And when we started, we wanted to decide what sort of network we were going to design, and we looked at three different scenarios. And as Ben said in the introduction, I've been working in CCS since 2006, and it's really interesting to see how models of pipeline infrastructure have changed over that time. So the first scenario, which we might think about, is we've called the each to their own scenario. Obviously, this is the most expensive option and impractical, but we kind of put it up there. But it is the least risky option in a way, because every emitter would be responsible for their own CO2 and pipeline operation. The onshore pipeline was considered to be separate, but the offshore pipeline was considered to be shared. As we've seen in various pictures that have been put up over the course of the presentations, there are only certain amounts of offshore pipeline landfalls to go from. So that's what we considered. The next scenario is our build it and they will come scenario. And this is where you have a central pipeline into which all the emitters feed. The phasing of the entrance into that system is interesting, and it's other work that Ben and I have published previously. The risk in this option is they don't come, and I guess that hopefully that risk is decreasing with the drive to net zero. Again, the offshore part of the scenario is shared. And then thirdly, there is the early adopter collaborator model. In this case, you have one early adopter who builds their pipeline, and there are then separate trunk lines that feed into that sort of gathering network. We considered that this was kind of a halfway house scenario between 1 and 2, and it kind of reduces the risk that that early adopter will be left with an oversized pipeline. Of those three options, the one that we've used to do our modelling is the build it and they will come model. So we have looked at all of the clusters and the emissions in that cluster, and said if somebody builds this, then it will be filled. It will be filled. So this is the assumptions that we had. We started with the main clusters. We did this before the phase 1. We started the work before the phase 1 clusters were really announced. So we looked at different sorts of scenarios. So in the paper, you'll see we've considered potentially a Northumber and Teesside option, and we've also considered a single South Humber option as well. And the idea of doing that was then each cluster is a building block, and we can build. Is that the one I'm meant to be using? We can build up the clusters into together, and then develop this TNS transport and storage sector. So that is the way that we have done it. So we have initially looked at track 1 clusters, and then we've done track 1 and the Scottish cluster, and now we're looking at and adding in the South Humber cluster as well. And the reason for doing that is primarily seeing how this sector might grow over time, and also thinking about how, I guess, the phasing of jobs and where they might be and where they might come on. So the methodology was to look at the total emission data for every cluster through the UK local authority and carbon dioxide emission statistics, to use a GIS base to map those emitters, and then to create onshore and offshore pipeline networks. There wasn't really anything fancy about how we did this, and we didn't. We took the landfall locations, but we used pipelines where we considered pipelines were feasible, and then we used shipping or shipping and pipeline where we considered shipping was a more feasible option. We also, because we were looking in Scotland, we also were able to explore the use of reuse of infrastructure options, particularly feeder 10 coming out of Grangemouth. And we developed CapEx and OpEx cost models, or we used project data where that was available. As we move forward and as clusters are able to talk more to us, we are hopeful of being able to add in real project data into this. Doing that, we built up from the bottom our sort of TNS sector. I just wanted to give you a little bit of an idea of how we modelled the pipelines, because you can get a wide variety of costs depending on how you model. For the cost models, we used 2 types of models. We used a diameter-based model, and we used a mass flow rate model. So primarily, the CapEx is based on the length of the onshore line and the diameter, the outside diameter of the pipeline. The outside diameter of the pipeline is driven by wall thickness calculations, but also flow rate calculations. And then the mass flow rate models take the mass flow rate and the length of the line with some fixed parameters. Now you'll see obviously this one here, given the constants in here, they tend to be quadratic fixed cost data. So they are the 2 models that we've used, diameter based and mass flow rate based models. For the shipping, now I've seen the presentation before mine. I think this is something that we can also input into our model as we go forward. But we used the ZEP model for shipping, and there was a high and a low cost for shipping from that ZEP model, depending on distance, as Jasmin has illustrated for us. And then we put our shipping clusters into these bounds to get approximate costs for shipping. And then finally, storage. Again, we did this in 2 different ways. There is limited data in the literature on storage cost models, and most studies are done based on feed analysis and using linear cost models again. Other studies presented cost models, but they combined the offshore pipeline element into that. For example, some work published by Pale Blue Dot. So we use 2 models again to give us bounding data. A linear cost model by Vandenbroek and Ramirez et al., which gives a CapEx for storage based on things like drilling costs, investment costs, the surface facilities, and so on. And we also used actual project-specific data to come up with our storage costs. This is just a summary of the cost for you. So I'm going to present cost models A and B, and the A and B models are shown here. And then the OPEX factor usually is just a factor which is applied to the CAPEX. So we did the same here, giving OPEX values, which we then applied on top of the CAPEX. So to give you an example for Grangemouth, you see this is what we were talking about, cement work, and this is feeder 10. So I picked this as kind of showing potential of how we could either use pipelines or shipping to St Fergus, how we can collect from maybe some distributed sources. And this is what I was saying about our refinements to the model going forward in terms of looking at other ways of doing this. But I want to put this example up because it shows maybe distributed sources, and it also shows reuse of infrastructure. And this gives you an idea of what is presented in the paper in terms of OPEX, CAPEX and OPEX costs for different models and different options that we have considered. And this allowed us to bound the CAPEX and OPEX costs for every cluster and every different option. And when we did that, we came up with this sort of analysis. So Grangemouth 1 and 2, Humber, and then we've got North Humber and Teesside and South Humber, and that is reflective of the time that we were doing this work. But it shows you the different CAPEX variations depending on the modelling approaches that you use. And as you might expect, the costs strongly align to the cluster size and the volume of CO2 and the complexity of the system. For OPEX, this again shows, and I think it's been shown in other presentations today, and I guess what Jasmin was saying at the end around OPEX for ship transport in particular. So if we look at two Thames clusters here, one for offshore pipelines where your OPEX is much lower, and one for shipping where your OPEX is much higher. But if you go back, the CAPEX goes the other way. It really depends on how those clusters are aligned, but we have built the building blocks to then be able to quite agilely bring in clusters as they develop. So what I wanted to show you, I guess, is more how can we use this techno-economic modelling, and this is where we have now been able to size a TNS sector and to think about how that TNS sector will expand in the economy, because at the minute that will be a new sector. The way we've modelled it is to say that it would be similar in terms of its inputs and outputs to that sector, to the oil and gas sector, but we just needed to know the size of that sector. So we've also assumed, as I said, this build it and they will come scenario. So we've assumed that it's initially oversized and that demand will be guaranteed. The important thing is who pays for this sector. So does the government pay for the sector by running a deficit? Or does the government socialise the costs? So we pay as UK households, as taxpayers, do we pay for this new sector? Or does the polluter pay, or the capture industry, do they pay? And is that paid through an indirect business tax? I just want to show you in the next slide what happens to the economy when you do this. So I think if you concentrate on, so up here we've got percentage change compared to the base year in GDP and employment. So the GDP are the heavy lines and the employment is the dashed lines. So you can see that most scenarios, or all scenarios, will give you an increase in GDP over time with in the initial stages, but that GDP will start to erode, depend on who pays, and in particular. Here we've got, just to highlight that if the government pays by running a deficit, then that GDP is maintained. Similarly with jobs, all options have the same impact in the first few years, but then if the government pays by running a deficit, then the employment is maintained. Whereas in the other two scenarios, it starts to drop off. The other thing about this work is it does indicate that we've put this sector into the whole economy, but it will not be impacted across the whole economy. So it will be impacted where those clusters are. So in terms of where jobs are realised and where jobs are lost and where the impact on households is realised will not be the same across the whole economy. So we have written a paper which kind of looks at this compared to other government policies, for example, on levelling up. So that was why I wanted to introduce you to our transport and storage model, not per se for the transport and storage itself, but to show how the sorts of techno-economic modelling that we do can be used to try and develop a T&S sector that we can then put into the whole economy, and the benefits that can accrue by doing that, and the sort of analysis that we can do. So I just want to finish with, so I've been doing this for, like I said, since 2006. And sometimes it has felt like, a bit like the quote from the Field of Dreams that if you build it, they will come. But hopefully now we're getting to a point where everything is starting to come together, and policy and whole economics are being informed by the excellent technical economic work that we've all been doing. So hopefully they will come, and we will build it. Thank you.
Thanks. Okay, do we have any questions for Julia?
Hi, Julia.
Hi.
I'd like to sneakily ask a couple of questions. In the economic model, is it a closed economy? Can we sort of import CO2/export the service of selling CO2?
Yeah, so that is something we particularly looked at in Scotland in particular. So this was work done as part of the Scottish Net Zero infrastructure project. So we did look at a possibility to export to be able to import CO2, so it will in that respect, yes, we can include that.
My other question was, this stretches my CG knowledge a little bit, but does the model kind of assume that the economy is already at sort of capacity, or at spare capacity?
Yeah, so we can do it. We can model it both ways, so that we can model it that it is at full capacity, so there's no unemployment, and or we can model it so that there are wage constraints and there is potential for wage bargaining. And that is the end of my CGE knowledge. But Christian Carvalho, who did most of the modelling here and is talking in the next session, he'll be able to answer those questions more or better. But yes, there is the opportunity to say, well, what happens if we can import employment capacity, or we assume that there is no migration of workers? We've done both. Yeah.
Okay, so sort of just on those two, you said that the model can do it. For the results that you showed,
Right,
did
yeah.
they export CO2 as a service, and were they sort of, you know, what assumptions do they have on capacity?
That I don't. Sorry, Erin, that I don't know. But it is in this first.
Yeah, thanks.
That's
Yeah.
the reference for it.
Anyway, I don't really have any, I don't know even know what CG stands for, so I'm really stretching my knowledge of this economic modelling, but we ran some similar modelling, economic modelling, Cambridge econometrics, and had this effect of the GDP and employment benefit kind of dropping off over time. And I guess there wasn't the option in that model to do this government deficit thing, which seems to have given a more nicer looking result. So I suppose my question is, yeah, because when you have taxpayer industry paying, there was this kind of knock-on economic negative effects after a while. So is there not some sort of catch to the deficit option? Like, if you were to show that to a policymaker, presumably they wouldn't simply believe that.
Yeah, so absolutely, and that's why we have been very engaged with BASE, as was there's the Department of Energy Strategy and Security and Net Zero, because just to inform the scenarios that we did run, because obviously if the government runs a deficit, then there is implications in other parts of the economy for that. So but yes, we have been bouncing this off government just to see, you know, how does this sit. Obviously, we've also been talking to people in the clusters around this industry pays, because certainly early on, when it wasn't so clear, the fact that industry had to pay for it, it did mean that would they do it, and or would they offshore, and would they take their business elsewhere? I think, and then particularly in Scotland, around Grangemouth, that would have significant social impact in that area. So I don't think I'm really answering your question, but yes, we, other than to say we have sense checked this across the two extremes of the model, from polluter pays or industry pays to government pays. No, I think it was for. I think it was for.
Any last questions from the room? No? If not, we'd like to thank Julia again.
Thank you.
So I think dispersed sites is a particular challenge for transport especially, and hopefully we've given you a few things to think about. I'd just like to thank you for all coming to the session and for all your contributions. Thanks.